Let us have a closer look at representations. Consider a sample representing two dimensions, the first dimension and second dimension. Let us say the sample is say 2, 1. 2 units on the first axis and 1 unit on the second axis. You can also understand this as a vector 2, 1. So the representation that we have as a vector in 2 dimensions, you should also appreciate the geometric interpretation of it. Now let us look at a line which is characterized by W, or we say this is W transpose X is equal to 0. What is W in this case? These are the coefficients of the first and second term. Or, so if you look at a numerical example, so this will be something like say -1, 2 transpose 2, 1 is equal to 0. This is the point. This is the line. What's the geometric interpretation of the W? W is -1, 2. Something like this. We know that they are orthogonal. A dot product is 0. So W in a way is a normal to the line. Now later on, when remember our objective is to learn W eventually. We have not started to talk about that problem. If you look at this expression, say W changes or W new is W old plus delta W. An incremental update of the W by an algorithm, by a learning algorithm. This means that we will be changing this W based on say a delta W to get you a new W. This will be your new W, this will be your old W. What does it mean to the line? Now the line will become something like this. So an update equation like this, when it changes the W, you can also visualize this W change as the change in the orientation of the line. Now we took this example in 2D. So we saw the example of say point and line. So what about if the sample was in 3D? This should have been a plane. Say a W in 3 dimensions. Or it could be a hyperplane. In a general d-dimensional space. So when we draw the line on the board, or when we use the word line and plane, in practice we imply it is a hyperplane in d dimension. To simplify the geometry and to draw on a piece of paper, we may be taking examples in 2D. But remember, in practice, we will be talking about a d-dimensional hyperplane, and a point in that space. Let us also look at one more equation before we end. See, we saw this representation of X transpose is a transformed version of the original features. This new representation, which is derived out of the old representation with the help of a matrix, which could be a learnable matrix, which could be computed in different forms, which could be assigned based on human knowledge. What's the implication of W? Depending on the nature of this matrix W, we can understand this as something that can do, say, rotation. Depending on certain properties of the matrix W, this could be understood as a rotation of the coordinate system. It could be a scaling. So we are interested in scaling one of the axes, maybe stretching, maybe compressing, and depending on the diagonal values of W, so it should change. Or non-uniform scaling. Or it could be more complex transformations like affine transformations. W could also be doing dimensionality reduction, say for example, like a so your X prime is in a new dimension and where D prime is less than D. This is important because maybe we are removing certain features which are not relevant to the problem and getting a compact dimension, compact representation, which is very useful. How do we know what representations are useful, what representations are not useful, or what features are useful, what features are not useful? We will see at later stage. But the modeling the problem as a matrix multiplication of X transpose is equal to Wx is a very powerful way of defining extracting the right features or the best features for our problem. Indeed, this need not be a linear transformation. So though we have used a linear transformation here, it need not be a linear transformation. It could be a quite complex nonlinear operation which derives a useful set of features from a set of raw features.